Everything strange about quantum mechanics, every paradox, every impossibility, every argument that kept Einstein up at night, comes down to one single experiment. Fire an electron at a wall with two slits. What happens next has baffled every physicist alive, including Feynman. Here's what should happen. The electron goes through one slit or the other, hits the detector screen. You get two clumps. Simple, logical, wrong. What you actually get is an interference pattern. Bright bands and dark bands, like water waves passing through two openings. But electrons aren't waves. They arrive one at a time, whole indivisible lumps. Click, 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 each one a single particle hitting a single point. So you think, fine, let me just watch which slit it goes through. Put a detector there, see the path, and it works. You see every electron go through one slit or the other. Mystery solved. Except now, look at the screen. The interference pattern is gone. Just two clumps. Exactly what you expected in the first place. When you watch, it behaves like a particle. When you don't watch, it behaves like a wave. Your observation changed the physical outcome. Not metaphor, not philosophy. Proven, repeatable, measurable physics. And the result changes depending on whether anyone is watching. Nobody really understands why. Not the way they'd like to. But I can tell you exactly how it works. And that turns out to be remarkably simple. Let me show you. In everyday life, everything makes sense. You throw a ball, it goes in one direction. You open a door. You walk through one doorway. Cause and effect. Logical. Predictable. You've spent your entire life building intuitions about how the world works, and those intuitions are completely wrong. At the atomic scale, none of it applies. Let me show you why. We're going to run 3 experiments, same setup each time. A source, a wall with 2 slits, and a detector screen behind it. Only the source changes. Experiment 1. Bullets. Imagine a machine gun firing at a wall with 2 narrow slits. Some bullets go through slit 1, some go through slit 2. On the screen behind, you get 2 clumps, one behind each slit. The patterns from each slit simply add up. No surprises, exactly what you'd expect. Experiment 2. Water waves. Now replace the bullets with water waves. Waves hit the wall, pass through both slits, and spread out on the other side. Where 2 wave peaks meet, they add up. Bright band. Where a peak meets a trough, they cancel. Dark band. You get interference stripes. Beautiful, predictable, and completely understood since the 1800s. So, bullets give you 2 clumps. Waves give you stripes. Simple enough. Experiment 3. Electrons. Fire electrons at the same wall. Tiny, indivisible particles, smaller than anything you've ever seen. What pattern do you expect on the screen? 2 clumps. Like bullets? You get stripes. Like waves. Now things get strange. This is the 2-slit experiment. Pay attention. This is the most important experiment in the world. You might think, okay, electrons are tiny. Maybe they're just some kind of wave. Maybe they flow through both slits at once, like water, and that's why you get stripes. Fair guess. But here's the thing. Turn down the electron gun, way down. Fire 1 electron at a time, 1 single electron. Then wait. Fire another one. Wait. Another. Click. 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 Each electron arrives at the detector as a single dot. A whole lump. Indivisible. It doesn't arrive as a smear or a spread. It hits one specific point. Just like a bullet. So you think, fine. They're particles after all. Each one goes through one slit or the other, Hits the screen, done. But now let the dots build up. Hundreds, thousands, tens of thousands of individual electrons, fired one at a time, each one arriving as a single point. And the pattern that emerges, dot by dot, click by click, is interference stripes. The same stripes you got with water waves. Stop and think about what that means. Each electron went through alone. There was nothing else in the apparatus to interfere with. No other electron, no wave, nothing. One particle at a time. And yet, stripes. What is it interfering with? Now let's make this precise. Here's a proposition. Call it Proposition A. Each electron goes through either slit 1 or slit 2. Sounds obvious. Must be true. It's a particle. It has to go through one or the other. There's no third option. If Proposition A is true, then the pattern on the screen should be the sum of two single-slit patterns. Two clumps. Like bullets. That's just logic. But we don't get two clumps. We get stripes. So either Proposition A is wrong, which seems impossible, or something else is happening that nobody can explain. Let's test Proposition A carefully. Let's put a detector at the slits and actually watch which way each electron goes. Let's test Proposition A the simplest way possible. Close slit 2 completely, block it off. Fire electrons through slit 1 only. What do you get on the detector screen? A single hump. Most electrons land directly opposite slit 1, fewer at the edges. Call this pattern 1. Now do the reverse. Close slit 1, open slit 2. Fire electrons. You get pattern 2, a hump opposite slit 2. Nothing surprising yet. So far, so good. Now, open both slits. If Proposition A is true, if each electron really does go through one slit or the other, then the result should be simple. Some electrons go through slit 1, make pattern 1. Some go through slit 2, make pattern 2. Add them together. That's what you should get. That's not what you get. Look at the center of the screen. Equal distance from both slits. With both slits open, lots of electrons arrive there. A bright spot. Now close slit 2, leave only slit 1 open. Fewer electrons at that same center point. Close slit 1 instead, open only slit 2. Again, fewer electrons at that exact same point. Stop and think about what that means. Closing a slit, blocking a path the electron supposedly didn't even use. Changed where it landed. At some points on the screen, you get more than twice as many electrons with both slits open compared to just one. At other points, you get almost zero, even though you got plenty with either slit open alone. This is interference. Exactly like water waves. Peaks reinforcing, troughs canceling. But these are particles, indivisible lumps, arriving one at a time. Click, click, click. The mathematics is simple, beautifully simple. You calculate it exactly like waves interfering, and the math works perfectly. But the physical meaning? How does an electron going through slit 1 know whether slit 2 is open or closed? Electrons arrive in lumps, like particles. But the probability of where they arrive is distributed like the intensity of a wave. Something doesn't add up, and the deeper you look, the stranger it gets. Now let's do something that seems clever. You say, okay, I want to settle this once and for all. I want to actually watch which slit each electron goes through. So you set up a strong light source right behind the two slits. When an electron passes through, it scatters a photon. You see a tiny flash of light. That flash tells you, this electron went through slit 1, or this electron went through slit 2. Perfect plan. Let's do it. You run the experiment. Fire electrons one at a time. Watch carefully for flashes. And here's exactly what you see. Every single time an electron arrives at the detector, click, you also see a flash of light, either near slit 1 or near slit 2. Never both at the same time, never halfway between. Every electron goes through one slit or the other. Proposition A is confirmed. Each electron really does go through one slit or the other. You can see it happening. You can watch which path it takes. Mystery solved then? Not quite, not at all actually. Look at the detector screen now. Look at the pattern. The interference pattern, those beautiful stripes, has completely disappeared, gone. What you see instead is exactly two humps. Pattern 1 plus pattern 2 added together. No interference. No stripes. Exactly what you'd get if you were shooting bullets. When you watch which slit the electron goes through, the interference pattern vanishes. When you don't watch, it comes back. Your observation has changed the experimental result, not your theory, not your interpretation. The actual physical pattern on the detector screen, the thing you can photograph, measure, count, is different depending on whether anyone is watching. This is not metaphor. This is not philosophy. This is repeatable, measurable, undeniable physics. Verified thousands of times in laboratories around the world. This result troubled Einstein deeply. He refused to accept it. He told Niels Bohr, the other giant of quantum physics, "God does not play dice with the universe." Bohr replied, "Stop telling God what to do." They debated for years, decades. Einstein kept inventing thought experiments, clever scenarios designed to prove quantum mechanics was incomplete, that there must be some hidden mechanism, some deeper explanation. And every single time, Bohr found the flaw in Einstein's argument. Schrödinger joined in with his famous thought experiment, a cat in a sealed box. Inside the box, a quantum event determines whether poison is released. Until someone opens the box and looks, according to quantum mechanics, the cat is simultaneously alive and dead. Sounds absurd. That was his point. Schrödinger wasn't explaining quantum mechanics. He was trying to show it must be wrong. A theory that says a cat can be alive and dead at the same time. That can't be right. But here's the thing. Every experiment we've ever done, every single one, confirms quantum mechanics. The predictions match reality to extraordinary precision. Einstein spent the last 30 years of his life trying to prove it wrong. He failed. The universe does play dice, and those dice follow rules that no one, not Einstein, not Schrödinger, not even Feynman, fully understands. But that doesn't mean we should give up trying to understand what's happening. Let's look more carefully at what observation actually does. Maybe the problem is simpler than Einstein thought. When you watch the electron, you shine light on it. Photons hit it. Maybe the light is just physically disturbing the electrons, knocking them off course. That would explain everything, wouldn't it? Reasonable thought. Photons are hitting the electrons, giving them little kicks, messing up their paths. That's why the interference disappears when you observe. It's not mysterious at all. It's just physical disturbance. So let's test it. Use dimmer light. Fewer photons per second. Less disturbance. Here's what happens when you dim the light. Sometimes an electron arrives at the detector, click, and you also see a flash. You know which slit it went through. But sometimes an electron arrives and there's no flash at all. The light was too dim. Not enough photons. Why no flash? Because light doesn't come as a continuous wave. It comes in lumps too, photons. When you dim the light, You're not making each photon weaker. You're sending out fewer photons per second. Sometimes an electron slips through without encountering a single photon. Now separate the results into 3 groups. Group 1. Electrons where you saw a flash near slit 1. Look at their pattern. No interference. 2 humps. Just like bullets. Group 2. Electrons where you saw a flash near slit 2. Same thing. No interference. 2 humps. Group 3. Electrons where there was no flash at all. You don't know which slit they went through. Look at their pattern. The interference is back. The stripes have returned. Stop and think about what this means. The electrons you tracked, no interference. The electrons you didn't track, full interference. Same apparatus, same light source, same everything. The only difference is whether you obtained information about which slit the electron used. This is not about physical disturbance. It's about information, about knowledge, about whether the path is distinguishable, even in principle. When you can know which slit, no interference. When you cannot know, interference returns. The universe doesn't care whether you actually look. It cares whether the information exists. And here's where it gets precise. Try using even longer wavelength light. Light that can't pinpoint exactly which slit. Something remarkable happens. Use longer wavelength light. Light whose waves are too spread out to pinpoint exactly which slit the electron passed through. What happens? Something beautiful. The interference pattern starts coming back. Not fully, not the crisp stripes you get with no observation at all, but partial stripes, blurred. Somewhere between full interference and no interference. Now make the wavelength even longer, even less information about which slit. The stripes get sharper, more defined, closer to the original pattern. Here's the remarkable thing. The correlation is exact. Quantitative. Perfect distinguishability. You know exactly which slit. No interference. No distinguishability at all. You have zero information about the path. Full interference. Partial distinguishability. Partial interference. The relationship is continuous and mathematically precise. Not approximate, not sort of, exact. And this leads to one of the most profound statements in all of physics. It is impossible to design any apparatus whatsoever that determines which hole the electron passes through, without at the same time disturbing the interference pattern. No loopholes, no clever tricks, no future technology that gets around it. This is fundamental. Now, you might think there's an escape. Maybe the electron really does go through one slit, and we just don't know which one. After all, when we look, we always see it at one slit. Maybe when we don't look, the same thing happens. We're just ignorant. That assumption, as reasonable as it sounds, gives the wrong answer. If you assume it always goes through one slit or the other, you predict 2 humps. Pattern 1 plus pattern 2. But that's not what we get. We get interference. The math doesn't lie. The assumption is wrong. You cannot save classical logic here. The universe doesn't work that way. Now stop and imagine something. What if these quantum rules didn't just apply to electrons? What if they applied at your scale? Imagine you're walking down a hallway. Ahead of you, 2 open doors, side by side. Behind those doors, a long wall. And someone is tracking exactly where you end up along that wall. Now apply quantum rules. You walk toward the doors. You don't go through one or the other. Somehow, and don't ask how, because nobody knows, you pass through both. And where you end up on the other side? Interference pattern Some spots you land frequently, other spots equally accessible, equal distance from both doors. You almost never land. Bands, stripes, just like electrons, just like waves passing through two openings. Except this is you, your whole body. Now someone puts a camera at the doors, watches which one you go through. Suddenly, you only go through one, every time. The interference pattern vanishes. You land in two clumps, one behind each door, exactly like bullets. Turn off the camera, stripes come back. Your path through a room depends on whether anyone is watching. Now, of course, this doesn't happen to you. Not at your scale. Quantum effects are unimaginably tiny at human size. You always go through one door. Always. But here's the thing that should really bother you. The reason it doesn't happen to you isn't because quantum mechanics stops working at large scales. It's because at your scale, the environment is constantly observing you. Air molecules, photons, thermal radiation, all bouncing off you, all carrying information about your position. You're being watched by the universe every instant. Quantum is the rule. Normal, your everyday experience, is the exception. The world you think is ordinary, it's the special case. So how do we actually calculate what happens in these experiments? How do physicists predict those exact interference patterns? The method is surprisingly simple. Here's how physicists actually do it. For every possible route an electron can take from source to detector, you assign a little arrow. Think of it as a clock hand. The electron leaves the gun, arrives at the screen. There are thousands of possible routes. Through slit 1, through slit 2, bouncing off the edges, even, in principle, going all the way to Andromeda and back. Every single route gets a clock. As the electron travels along each path, its clock hand spins. How fast it spins depends on the electron's energy. How far it spins depends on the path length. When the electron arrives at the detector, you look at where each clock hand is pointing. Now add up all the clocks, all possible routes, every single one. The arrows that point in the same direction reinforce each other. They add up to a longer arrow. The arrows that point in opposite directions cancel each other out. The length of the final combined arrow, squared, gives you the probability. That's it. Where clock hands align, high probability. Bright spot on the detector. Where they cancel, low probability. Dark spot. Interference pattern. Explained. Calculated. Precise. Does the electron really take all those routes? Does it actually go to Andromeda and back? I think the answer is yes. That's what the mathematics tells us. We know how to calculate. We get the right answer. Every time. To extraordinary precision. But what it means, what's really happening between the source and the detector, nobody understands the way they'd like to. We know the rules. We don't know why those are the rules. But these rules, amplitudes, interference, uncertainty, they're not just abstract physics for a laboratory. They're holding you together right now. What is an atom? A positive nucleus surrounded by negative electrons. Opposite charges attract powerfully. So here's a question that should bother you. Why don't the electrons just crash into the nucleus? Classically, they should. Opposite charges attract. The electron should spiral inward, lose energy, and collapse onto the proton. Every atom in the universe should have self-destructed billions of years ago. But they didn't. You're here. Your atoms are stable. Why? The uncertainty principle. Suppose the electron did sit right on the nucleus. You'd know exactly where it is, pinned to one tiny point. But remember what we learned. If you know the position precisely, the momentum uncertainty becomes enormous. The electron would have so much kinetic energy, it would immediately fly away. So the electron compromises. It doesn't sit on the nucleus. It doesn't fly away. It finds a balance, spreading out just enough that the position uncertainty is manageable and the momentum uncertainty stays reasonable. The result? The hydrogen atom has a radius of about half an angstrom, roughly 2/billionths of an inch, or about 50 trillionths of a meter. And its energy is about 13.6 electron volts. Calculate this from the uncertainty principle. You get the right answer. Not approximately, precisely. And here's why this matters to your daily life. Try to push two atoms closer together. You're confining electrons to a smaller space. By the uncertainty principle, their momentum increases. Higher momentum means higher energy. Energy that resists compression. Pushes back. That's why your hand doesn't pass through the table. That's why the floor holds you up. That's why solid matter exists at all. Quantum mechanics. The same weird rules that say electrons go through both slits is the reason you don't fall through the floor. Now think about the electron wave confined inside the atom. You know what happens when you confine a wave? Think about sound in an organ pipe. Blow air across the pipe. You don't get every frequency. You get specific notes. The pipe has a fixed length and only certain wavelengths fit. Fundamental frequency. First harmonic, second harmonic. Specific, discrete, quantized. Same thing happens to an electron confined in an atom. The electron wave can only have certain wavelengths, certain frequencies, certain energies. Lowest energy, the ground state. The electron sits there, stable. Higher energies, excited states. The electron is temporarily in a higher mode, like a higher note in the organ pipe. An excited atom eventually drops back down, and when it does, it releases light. But not just any light. Light with a very specific frequency, determined exactly by the energy difference between the two states. That's why neon signs glow red. Sodium streetlights glow orange. Hydrogen emits specific lines that astronomers use to map the universe. Each element has its own fingerprint, its own set of allowed transitions, its own colors. None of this makes sense without quantum mechanics. Without quantized energy levels, atoms would glow every color equally. White noise. No fingerprints. No chemistry as we know it. And here's something beautiful. The uncertainty principle, position times momentum greater than or equal to a fixed number, isn't because of our measurement. It's because of waves. Short wave packet, well localized, but it's made of many wavelengths, many possible momenta. Long wave packet, nearly one wavelength, nearly one momentum, but spread out over a huge distance. You cannot have both, not because of technology, because of mathematics, because of what waves are. Here's why this matters to you personally. Right now, the device you're watching this on contains billions of transistors. Every single one works because of quantized energy levels. The exact same principle Feynman just showed you with electrons confined like standing waves in an organ pipe. Without quantum mechanics, no transistors. Without transistors, no computers. Without computers, no internet. Without the internet, no this video. The chain is direct, unbroken. And now, scientists are building quantum computers that use interference directly. The same interference from the two-slit experiment. Quantum bits that exist in superposition, like an electron going through both slits at once. They're using the weirdness to solve problems that classical computers never could. The strange rules aren't just strange, they're useful. They're essential. They're running your life right now. Every text message you send, every photo you take, every video you stream, quantum mechanics. Working exactly as Feynman described, amplitudes, interference, quantized energy, inside a chip smaller than your fingernail. Things on a very small scale behave like nothing you have direct experience with. Not like waves, not like particles, like nothing you've ever seen. Things on a very small scale behave like nothing you have direct experience with. They don't behave like waves. They don't behave like particles. They don't behave like clouds, or billiard balls, or springs, or anything you've ever seen. Quantum mechanics describes nature as absurd from the standpoint of common sense, and yet it agrees fully with experiment. Let me tell you what we've seen today. We fired electrons at two slits. They arrived as particles, click, 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 but built up a pattern like waves. We tried to watch which slit they went through. The pattern changed. We dimmed the light. The electrons we tracked, no interference. The ones we didn't, interference returned. The universe doesn't care whether you look. It cares whether the information exists. We showed you that this isn't about disturbance. It's about distinguishability. And the relationship is exact, mathematically precise, experimentally verified, no loopholes. We imagined quantum rules at your scale, you walking through two doors, your path changing because someone put up a camera, absurd at your size, but only because the universe is constantly watching you. Quantum is the rule. Your experience is the exception. We showed you how physicists calculate, little clocks spinning along every possible path, adding up, canceling out. The math works perfectly, every time, to extraordinary precision, and we showed you why it matters. The uncertainty principle is the reason atoms have size, the reason your hand doesn't pass through the table, the reason neon signs glow red and sodium lights glow orange, the reason the device in your hand works at all. Quantum mechanics is not a curiosity locked in a laboratory. It is the operating system of the universe. And nobody understands it. Not the way they'd like to. Feynman said it best. I think I can safely say that nobody understands quantum mechanics. But here's what I hope you take away. You don't need to understand why the rules work to appreciate that they work. And to see, really see, how extraordinary it is that a universe built on uncertainty, probability, and interference patterns managed to produce you, sitting here, watching this, wondering about it. That's the beauty of physics. Not comfort, not simplicity. Truth. If this changed the way you think about reality, even slightly, subscribe. There's more to come. Things about space, time, light, and gravity that are every bit as strange as what you've seen today. And if you want to go deeper into the two-slit experiment, I'll leave a link in the description. Thank you for watching.